All right, I wanted to finish up section 3.3. We're talking about the derivatives of the trig functions. In the previous video, I had shown you two limit calculations that we needed to know in order to be able to prove that the derivative of sine x is cosine x. Using similar methods, you can show that the derivative of cosine x is negative sine x. Okay, and that's where we had left off here. Now, in this next example, the derivative of tangent x, so tangent x, that's the same as sine x over cosine x, right? And the fact that I could look at this as a quotient means that I could use the quotient rule. So we talked about the quotient rule in the last section. The quotient rule will come up a lot. I mentioned in the last section, make sure that you memorize that. It'll come up a lot. And so I'm going to use that now. Okay, well, I want the bottom times the derivative of the top minus the top times the derivative of the bottom all over the denominator squared. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Okay, and cosine x times cosine x, well, that'd be cosine squared x. Negative sine x times negative sine x, that'd be sine squared x. Cosine squared x plus sine squared x, that's 1, right? That's my Pythagorean identity. And 1 divided by cosine x, well, that would be by definition how I define secant x. So 1 over cosine squared x, that would be secant squared x. Okay, the derivative of tangent x is secant squared x. How about the derivative of secant x? Well, secant x is defined as 1 over cosine x. And I could look at it like that. That's how I'd want to look at it, because then I could use the quotient rule again. So let's apply that now. The bottom times the derivative of the top, the derivative of 1 is 0, minus the top times the derivative of the bottom, the derivative of cosine x is negative sine x, all over the denominator squared. The first term would go to 0. So you're going to have 0 plus sine x all over cosine squared x. Cosine squared x, same as cosine x times cosine x. 1 over cosine x is how we define secant x. Sine x over cosine x is one way to look at how we would describe tangent x. Okay, so the derivative of secant x is secant x times tangent x. The derivative of cosecant x and cotangent x can also be found by using the quotient rule, along with their quotient identities. So cosecant x is the same as 1 over sine x. You could use the quotient rule then. Cotangent x is the same as cosine x over sine x, and again, you can use the quotient rule. All right, now here's the derivatives of the trig functions. So we've already looked at, the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Make sure that you got the sign there. And then the derivative of tangent x is secant squared x. The derivative of cosecant x, if we were to calculate that, would be negative cosecant x cotangent x. The derivative of secant x, we've done that, right? That is secant x times tangent x. The derivative of cotangent x, if we were to calculate, would be negative cosecant squared x. Memorize these. Okay, these all 6 of these will come up all over the place. Okay, now if you happen to forget one, I feel like calculating a derivative of any one of these 6 is very easy to get. Okay, as long as you know the derivative of sine x is cosine x and the derivative of cosine x is negative sine x. On the other 4, you're using the quotient rule. Okay, but I would say memorize these. Okay, they're going to come up a lot, like I said. So let's take a look at some examples. Okay, suppose that we want to find the derivative of y equals x squared times sine x. Well, that'd be a product rule, right? Since I'm multiplying. And so let's use the product rule now. We want the first, which is x squared, times the derivative of the second. Derivative of sine x is cosine x, plus the second, sine x, times the derivative of the first. Derivative of x squared is 2x. And Okay, that's my answer. I guess I pulled the 2x term in front of the sine x term. You didn't need to do that if the parentheses were there. Yeah, so that'd be my answer. Okay, here's another example. F of x equals secant x divided by 1 plus tangent x. Let's find the derivative. So this would be a quotient rule. The bottom is 1 plus tan x times the derivative of the top. Derivative of secant x is secant x tangent x. And then minus the top is secant x times the derivative of the bottom. The derivative of 1 is 0. The derivative of tan x is secant squared x. And this is all over the denominator squared. Okay, now from this point, we want to simplify. Secant x is in common to these two groups. So let me go ahead and factor out a secant x from those two groups. And I could also distribute the tangent x into these two terms here. So once you've factored out secant x, you're going to have tangent x plus tangent squared x, and then minus secant squared x from over here. Okay, now secant squared x minus tangent squared x is equal to 1. That's another Pythagorean identity. Make sure that you know that. It will come up. Using this identity, okay, if you were to multiply both sides by -1, tangent squared x minus secant squared x would be -1. Okay, so where I see that part, let me replace that with a -1. And everything else can stay as is there, and that'd be as simplified as we can get it. Now, sometimes when you work with derivatives and the trig functions, you'll need to use identities. Okay, it's just part of the simplifying process here. You know, an identity might come up here and there. Make sure that you know your Pythagorean identities. Okay, any other identities are not worth memorizing, in my opinion. And all they're very easy to just look up in a book. Okay, you'll want to consider using at least your common identities, like your Pythagorean identities or quotient identities. Okay, because it makes simplifying then easier. All right. And I've mentioned several times here how your book is going to want you to be simplifying as far as possible. Okay, now you're going to want to do this anyway because later on when we're doing lots of simplifying for solving equations and looking at application problems, we're going to want our calculation to be as simplified as possible if we're solving for x or something like that. Okay, so just consider that for what's down the road. Make sure that you're simplifying. Okay, here's another example. G of theta equals 1/3 cosecant theta minus e to the theta times cotangent theta. Let's find the derivative of g. G prime of theta, well, the first term here, 1/3 is a constant, right? And the derivative of cosecant theta is negative cosecant theta cotangent theta. And then minus, the second part is going to be a product rule. So, and I'm subtracting the whole thing, which means I'd want brackets around this part that I'm going to subtract. The first is e to the theta times the derivative of the second, derivative of cotangent theta, is negative cosecant squared theta. Okay, plus the second is cotangent theta times the derivative of the first, derivative of e to the theta is itself e to the theta. Okay, and I guess the only thing I can do to simplify that would be to distribute the negative here into these two terms. And so that's what I've done here on the next line, just distribute the negative. And go ahead and circle that result. That would be my answer. Okay, if we go to the next page here, here's another example. Suppose that f of t is equal to secant t, and I want us to calculate f double prime of pi over 4. Well, the first thing I'll have to do is I'll have to get f double prime of t. Okay, and if we calculate f prime of t, the derivative of secant t is secant t tangent t. Okay, so then if I take a derivative of that, to get f double prime, I'll be using the product rule. So it's the first is secant t times the derivative of the second. Derivative of tangent t is secant squared t, plus the second, that's tangent t, times the derivative of the first. The derivative of secant t is secant t tangent t. And let's simplify that. So if I multiply these terms, I'm going to have secant cubed t, and then plus secant t tangent squared t. Secant t is in common to these two groups, so you can factor that out of the whole thing. Secant squared t plus tangent squared t, that'd be my leftover. Secant squared t plus tangent squared t is nothing. Okay, now secant squared t minus tangent squared t, that'd be 1. Some students would mess this up and they'd say this is 1 when in fact it's not. Okay, this is as simplified as I can get it. Okay, so of course know when to use the identity and use it correctly is the message that I'm putting there. Now I want us to find f double prime of pi over 4. Well, I've got my formula here, so I just plug in pi over 4 and simplify. Okay, so secant pi over 4. Well, cosine pi over 4 is 1 over root 2. Secant of pi over 4 would be the reciprocal of that, so I'd have root 2 over 1. Okay, times secant squared pi over 4. Well, secant pi over 4 is root 2, what we just said. I'm going to square that number, and then add tangent squared pi over 4. Tangent of pi over 4 is 1. 1 squared is 1. Okay, root 2 squared is 2. 2 plus 1 is 3. So we get 3 root 2 is the exact output there in the problem. And, like the other things that we've been doing, make sure that the answers are in exact form. Okay, don't do anything with decimals unless you're told to do things with decimals and rounding and stuff like that. Exact answers. Okay, there's a couple of limit questions mixed in towards the end in the homework. I had mentioned, these two limits that we had looked at earlier that were helpful in showing that the derivative of sine x is cosine x. But consider those for some of the other limit questions there at the end of this section. Let's take a look at just one example here. Find the limit as x approaches 0 of sine of 4x divided by sine of 6x. Okay, well, of course I can't cancel anything since the angles are different there. I can't plug in 0, right, because sine of 0 is 0. I know I can't divide by 0. So there's going to be, some algebraic manipulation going on here. Now, a strategy that I'd want to consider is I'd want to consider kind of rewriting this into a form where I can use a previously known limit, okay, and or use some trig identity stuff. So let's see, if I were to multiply the top and the bottom by x, then there's no harm with that, right? X over x is 1. Okay, let me also multiply the top and the bottom by 4, and I'll multiply the top and the bottom by 6. I'm also going to split this limit into two limits. Okay, now 4 is a constant that can come out of the first limit, and the limit as x approaches 0 of sine of 4x over 4x. Well, let's see here. So if I go back to this very first limit, the limit as theta approaches 0 of sine theta over theta, that's 1. Now theta is an angle. Here I've got 4x. So what? But 4x is the angle, right? The angle, 4x, is matching what I've got written in the denominator with that also being 4x. So the value of that limit, therefore, would be 1. Okay, so I've got 4 times 1 times, now with this second limit here, 1/6 can come out of the calculation, and 6x divided by sine of 6x, that'd be the leftover inside the limit still. And if I were to write sine of 6x divided by 6x to the negative 1 power, that would be the same as 6x divided by sine of 6x. Now, the limit of an expression raised to a power is the same as the limit of the expression, whatever that is, and then taking care of the power at the very end. So the limit as x approaches 0 of sine of 6x over 6x, that would be 1, right? Again, I'm using this previously known limit here. Theta is an angle, and so here I've got 6x. That's fine. 6x is my angle, which matches what I see in the denominator. 1 to the negative 1 power is 1. 1 to any power is 1, right? And so I end up getting 4 times 1 times 1/6 times 1. Or 4 over 6 reduces to 2/3. 2/3 would be my answer. Okay. So, like I said earlier, with the couple of limit calculations there at the end, consider using the limits that we had looked at earlier in this section, if possible. I know on some of them for sure you'll be using them when you're doing the calculation there. Okay. Also, the more important thing, make sure that you know the derivatives of the trig functions. Memorize these. Super, super important. We will be using them a lot as we go along in the course here. All right, definitely look at the homework. The homework is on page 196. Be sure to look at the odd numbered problems listed there for me.